Our first major topic for empirical research has to do with constructs and categories. And to talk about research on constructs and categories, we have to also talk about measurement. So in this session, I want to introduce you to some basic principles of measurement. And what kinds of questions about constructs and categories might we have? Well, first of all, constructs are the main ideas or phenomenon of interest to us. And we can develop constructs about virtually anything. Here we're likely to be interested in specific aspects of human experience, whether that's behavior, emotion, cognition, or relationships. We might be interested in certain characteristics of social groups, or social institutions, or interactions with our natural and built environments. We often use categories in thinking about constructs because these define subsets or subgroups which represent different types, forms, or variations of a phenomenon of interest. So here's some questions about constructs and categories. A good question: how is transphobia conceptualized, defined, and measured? This is a very interesting article. It's a letter to the editor discussing different measures of transphobia and the problem that they use very different content and very different definitions of transphobia. So there's no clear consensus across studies about what transphobia means, how it should be defined. That's a very interesting issue and problem. Here's another topic. How can we assess distress among people in community settings, not in hospitals or in clinics? And this article takes a look at 8 different measures of psychological distress and their characteristics or psychometric properties of these different measures. So good constructs are measurable or potentially measurable. I said before that some studies use nominal and operational definitions to turn constructs into variables and measures. So nominal definitions, again, are like dictionary definitions in that they define terms in other words or synonyms or sometimes phrases. Again, multiple nominal definitions are possible for any given construct. So, for example, income inequality could refer to differences in income, or it could refer to differences in wealth. Operational definitions indicate how a construct is measured in a particular study. Again, with no single right or wrong way to do this, but this is what turns a construct into a variable. Again, multiple operational definitions are possible. For example, there are multiple measures of depression. Different depression scales measure this construct differently. Okay, so let's take some constructs and think about their nominal and operational definitions and what they look like when measured in terms of variables. So again, using this construct of clinical depression, a nominal definition of this construct can be found in the DSM-5. This is quite a complex definition, so I'm not rehashing it here, but the DSM-5, the Diagnostic and Statistical Manual of the American Psychiatric Association, the 5th version of it, has specific criteria for clinical depression. It says you have to have a certain number of signs or symptoms of depression within a certain period of time in order to be diagnosed with various forms of depression. Clinical depression is operationally defined in various ways. So, for example, the severity of depression is assessed with the Beck Depression Inventory, and it's assessed with a number of questions. There are, I think, about 20 questions that are asked, and people are given scores based on their answers to those questions. And they get an overall score on the BDI, the 2nd version. The scores range from 0 to 63. And there are certain norms in terms of how these scores are used, so that the variable, the BDI score, means certain things. Value under 13 is minimal depression, and the clinical cutoff for severe depression is 29 or above. On a completely different topic, we have this construct of economic inequality, which can be nominally defined as the difference between the richest and poorest people in a country in terms of their income or wealth. Again, we're going to have to pick one or the other. And in many studies, that is operationally defined in terms of a Gini coefficient, and we can create a Gini coefficient, which I'll explain in a second, using either income or wealth. But on the right, you can see that the variable, the Gini coefficient, ranges from 0, which means perfect equality. Everyone has exactly the same income or exactly the same wealth, which never happens, to 1, which is perfect inequality. No one has the same income or wealth. Everyone is different. That also doesn't exist. So scores range from 0 to 1 with many values around 0.3, 0.4. Okay, your turn. Identify and define some constructs of interest to you. So think of a couple of constructs. How might you nominally define them? What might some operational definitions be? And what kinds of variables can you envision using to measure these constructs? So come up with this on your own, and then let's talk about this in class. Okay, again, we're working now with building blocks of structured research. So I want to make clear that there are differences between variables, values, constants, and cases. Let's play around with these ideas for a bit. So a variable represents a construct, and by definition, it must take on different values. That is, it must vary. Values are the different numbers or properties that a variable can take on. So for example, if the variable is numeric, then numbers or values that are possible might range from, let's say, 0 to 10. So any value between 0 and 10 is perhaps a legitimate score on that variable. But variables don't have to be numeric at all. So the variable religious affiliation has different values, and those values are the names of different religious affiliations: Buddhist, Taoist, Catholic, Jewish, Islamist, and so on. Constants are features that remain unchanged within a study. So a constant is what happens when a variable does not vary. It's constant. And cases are our units of observation. So cases are not necessarily people. They might be. If a study of people will often use people as cases. But a study of households will use households as its units of observation. Or you could do a study of agencies, or states, or countries. So we can use these ideas of variables, values, constants, and cases somewhat flexibly in research design. And you have to understand that in order to understand how studies are conducted. So let's use a couple examples. Let's say you're studying the household composition of families who appear in a social service agency. So families are coming in as units, and the question is, what are their households like? So variables of interest here are variables that describe the household composition. They could include things like the number of adults in the household, the number of children, their relationships among people in the household. Here, the agency is a constant in this study, because we're only studying families seen in one social service agency. And the cases are families. Okay, these sort of units can shift in a different kind of study. So let's say you're studying the caseload size for all social service agencies in a county. So now you have multiple agencies. Each of them has a different caseload size, and they're all within one county. So caseload size is a variable. The number of cases for each agency is a value. The county is a constant. And the cases, or units of observation, are agencies. I want to talk with you about how we move from concepts to definitions and measurement. So as we've said before, nominal and operational definitions turn concepts into variables that can be measured. And variables produce data on, measures produce data on variables of interest. Data are often stored in matrices organized by variables and cases. And it's important to be able to visualize this so that you understand what's going on behind the scenes here. So this is a typical data matrix, again organized by cases and variables. Cases are shown in rows, and variables are shown as columns. That is the typical way in which data are arrayed. The cells contain data or the values for each case on each variable. We might, of course, be missing data in some cells. I want you to think a little bit more about good measures of constructs, and one principle articulated by Kurlinger and Lee is that a good measure is isomorphic to reality. An isomorphic means that it shares the same form as something else. So a measure of a construct is not the same thing as the construct in reality. It is a measure, after all. But a good measure will look like the construct in reality. It will be like a mirror image. So if the construct in reality has, let's say, 5 letters, A, B, C, D, and E, then the measure of that construct should have those same values in the same order in the same place. And operational definitions, which indicate how properties of a construct are mapped onto measures, should provide an accurate map of the construct. So this is an accurate map, or what we think of as a valid measure. It is isomorphic. It reflects the way we understand the construct. This is a map that's inaccurate, invalid. Here we are confused. So here the values of the construct are not being accurately mapped onto our measure. We have an invalid measure. Another important feature of measures of constructs has to do with levels of measurement. And there are 4 levels of measurement. LOM is a common abbreviation, and we can remember them with the acronym NOIR, nominal, ordinal, interval, ratio, NOIR. So nominal measures have values that are different in name only. Ordinal measures have categories that can be ordered from greatest to smallest or best to worst, but they're not really numeric. Interval level measures are numeric, and they have equal intervals between adjacent values on the scale. So the difference between a 1 and a 2, for example, is the same as the difference between a 2 and a 3. Those are equal intervals. And then a ratio measure is an interval scale with a true 0. So 0 has some real meaning on that scale. Let me give you some examples. So nominal measures, again, that differ in name only, include things like religion, or religious affiliation is a variable where the values differ in name, Catholic, Protestant, Lutheran, etc. Gender has differences in type only, ethnicity, or mental disorders. So nominal measures are useful for many purposes, and problems arise in nominal measures when the categories or subtypes that we're using overlap. So one principle of measurement is that categories should not overlap. They should be mutually exclusive. Another problem arises when our nominal measure does not capture all possible categories, meaning that it's not exhaustive. A good measure is mutually exclusive and exhaustive. So an example of that last problem occurs when we ask about gender and we give 2 options, male or female. That's not an exhaustive measure because it excludes lots of other possibilities, other responses to the questions about gender. We can finesse that a bit, solve the problem superficially, by adding an other category and allowing people to fill in the blank. So here, if I ask for a response on gender and I ask for male, female, and other, in theory I'm including all possibilities, although that's a rather simplistic way to do it. Ordinal measures, again, have categories that can be ordered or ranked from greatest to least, or best to worst, or most frequent to least frequent. You see this a lot in opinion scales, where you're asked to strongly agree, agree, disagree, strongly disagree. There's an order to that. Problems occur in ordinal measures when we don't capture all possible options. For example, if I have absolutely no opinion on this question and you've asked me to agree or disagree, I don't know how to answer it. Problems also arise when we treat ordinal scales as if they're numeric. So sometimes you'll see this, that 1 equals strongly agree, 2 equals agree, 3 equals disagree, 4 equals strongly disagree. I mean, that's okay if you're just asking me to pick a number. But if you're pretending that strongly agree equals 4, and you're saying that's twice as much as agree, yeah, that doesn't make sense. So they are not inherently numeric. And we can't really perform mathematical operations on ordinal scales. Interval level measures are numeric. They have equal intervals between adjacent values. So examples are the size of objects in height or width. An object, by definition, has some height or width, and we could measure it in millimeters or pounds or kilos. Another example is household size. The size of a household ranges from 1 to some larger whole number. There are no households with 0 members or half members. Some interval scales have negative numbers. For example, there are some scales of socioeconomic status where the midpoint, the middle of the scale, is the poverty line. It's not a real 0. It doesn't mean that people have no income or SES. There are numbers above and below the poverty line, and there are equal intervals between those numbers, but there's no real 0. And then a ratio measure does have a true 0. It's an interval scale in which 0 really is possible and means something. So as an example, the number of children per household is a ratio measure. You could have 0 children or 1, 2, 3, or 4, and so on. There's an equal interval between each point on the scale and a real absolute 0. So here's a summary of what I've just said, really. Properties of good measures by level of measurement. So on the left you see our noir levels of measurement. And then I've shown you in a more systematic way the characteristics of good measures of these types. So again, I said that a nominal measure should have mutually exclusive, that means not overlapping, categories. So each case will be in one category or another. And it should be exhaustive, covering all possibilities. Now those two characteristics are characteristics of all good measures: mutually exclusive categories and exhaustive. Then when we move to ordinal measures, we add the characteristic that values can be rank ordered. Interval measures, again, have equal intervals between adjacent values on the scale, and ratio measures have an absolute 0. Okay, there's another way to think about variables, in that these can be dichotomous, discrete, or continuous. So a dichotomous variable has only 2 categories, and these are usually scored 0 or 1. These are also called dummy variables when they're scored 0 or 1. And they're useful for capturing some characteristics and events. For example, is a child living with a biological parent? No or yes. No is typically 0. The event is not occurring. 1, yes it is. Is the participant age 18 or older? No or yes. Then there are discrete variables that can take on only certain values. So for example, if I ask for age at the last birthday, I'm asking for age in years, and only whole numbers are possible. In contrast, continuous variables have really infinite possibilities because they include all values within a scale. So if I just say, how old are you? Your response could be in years, or you could give me years in months, or years, months, days, hours, minutes, seconds, and if you're really accurate, nanoseconds. Okay, so these are 3 different types of variables. The variable format really depends on how you ask the question and frame the answers. So for example, if I ask, how many children do you have? I could frame your answers as a dichotomous measure, none or some, no children, some children. Or I could frame it as an ordinal, a discrete ordinal measure. 0 means you have no children, 1 means you have 1 child, 2 means you have 2 children, 3 means that you have 3 or more children. So it's not an interval scale. It's not a equal interval scale, but it is an ordinal measure. Or I could frame the answer as a discrete ratio measure, counting the number of children from 0 to a whole number. So the way we frame answers matters a great deal in terms of the format of variables and data. Let's now talk about how data are stored and what we can do with them. Now, here I'm talking about qualitative data. We'll come to quantitative. I'm sorry, I'm talking about quantitative data. We'll come to qualitative data in a little while. But for quantitative data, we often array this again in a matrix. And here we have case IDs. Cases are rows, and instead of numbers, I've used names to show that these are people in this case. And let's say we have 2 variables. I'm going to call them X and Y. And for each case, we've acquired a value on each of these variables. So this is a data array for 2 variables, X and Y. Now I'm going to show you a frequency distribution that shows you the number of cases, small n, with each value of X in this data set. So I show in the first column the different values of X, and in the second column the number of cases with that value of X. That's a frequency distribution because it shows how frequently each value of X appears in the data set. Now I do the same thing for Y. So I'm showing you different values of Y and the frequency, the number of cases, with each of those values in the data set. This is an important building block because when we take the next step, we're going to graph this data, and that's called a histogram. So this is the same data, but instead of a frequency distribution, I'm showing you this in a graphic representation, histogram. So now I'm showing you in the top histogram the values of X on the horizontal axis, that is also called the x-axis, and the frequency or number of cases on the vertical or y-axis. And that's a graphic distribution of the frequency distribution of X. And below it you see a picture of the frequency distribution of Y. Now this is an important building block. Why? Because in large samples, this is where we get bell-shaped curves. So what's underneath a bell-shaped curve is this kind of frequency distribution. That's what the curve means. It's looking at how often different values of the variable represented on the horizontal axis occur in the data set. Now these distributions aren't always normal curves. We'll talk about that now. Distributions again show all the values of a variable in a sample. We have the standard normal bell-shaped curve shown here in red. Don't worry about the Greek letters. And then other kinds of curves, tall ones, flat ones, off-centered ones. We use descriptive statistics to illustrate different trends in a data set. And let's start with measures of central tendency. These are different kinds of averages. So when we talk about average, we're often talking about the mean, that is the arithmetic mean, which is the sum of all of the scores in the data set divided by the valid number of cases. I should say sum of all of the scores on a variable divided by the valid number of cases, because we're dealing with one variable at a time. A different way to think about average is the median. And the median is the point at which half of the scores are above and half of the scores are below that value. And the mode is the most common score in a distribution. In a normal bell-shaped curve, the mean, median, and mode are all the same, but that's not always the case. Another type of descriptive statistic has to do with dispersion or variability. So measures of dispersion really describe how closely the scores in the data set how closely they are distributed around the mean. So here you see 3 different distributions one of an IQ verbal score, one of a math score, and one of a spatial recognition scores. And you can see that there's less dispersion, less difference in the first distribution. Most of the scores are pretty close to the average. And then around math scores, there's more variability. And in spatial recognition, there's even greater dispersion. So these measures of dispersion or variability include the standard deviation, which is used to describe sample data, and the variance, which is the standard deviation squared. But when we're talking about population data or population estimates, we use the standard error, which is calculated a little differently, and the variance for population estimates is the standard error squared. So just remember, standard deviation is used for describing sample data. Standard error is used for making estimates about population parameters. Okay, we also have another descriptive statistic called skew, and skewness is the extent to which the distribution is slanted to one direction or another. So for example, income distributions tend to be very positively skewed. That would be like the distribution on the far right, where a few cases have very, very high values of income, and most cases are down toward the bottom or at the bottom. And in these cases, you see that the mean, median, and mode are not the same, while in a normal distribution, they are exactly the same in a bell-shaped curve. So let's work with these ideas a little bit more and think about differences between mean and variance. What do these things imply? And an example I'm going to use has to do with climate change. So when we say there is climate change, what does that mean? Does that mean our weather is getting hotter over time? That would be an increase in mean average temperature, like the diagram at the top. It shows that our previous climate, with examples in blue, has an average temperature that is less than, over to the left, smaller than, the average temperature of our new climate. So the weather is getting hotter. Or does climate change mean that our weather is becoming more variable? That's what would happen in the middle diagram. The average temperature might stay the same, but there's an increase in the temperature variance, in the variability of the distribution. So we have more record cold days and more record hot days if the weather is becoming more variable. Or is it possible that climate change means both? That both the average and variance in temperature are increasing? And if that's the case, then we have more hot weather and more record hot temperatures. What's the answer? Here's the data on climate change showing that our weather is getting hotter, not more variable. So we've graphed this since 1960, not a very long time, but it shows that since 1960 the average temperature is increasing. Of course, there's some variation there. It's not a straight line. But when you map variability over time, it's not that different. So I hope this gives you a sense of how we think about changes in average versus changes in variation. Then descriptive data are used to understand characteristics of samples. So here, for example, we have data on household income, credit card debt, and other debt in thousands of dollars in households. And you see tables like this all the time in research reports, so it's important to understand how to read this. So the mean, the arithmetic mean or average, means that on average in this sample, the household income is almost $60,000, with average credit card debt of about $2,000 and other debt in close to $4,000. The standard deviation, or the variation, is very high for income. So household income is highly variable. At $69,000 is a standard deviation. That's a very high number, almost as high as the income itself. Credit card debt is to almost $3,000 is the standard deviation. Other debt, almost $5,000, so a little more variation in other debt. The N is the number of cases in this sample that provided valid data, 15,000 households. And then you can see median income, 40,000. Median credit card debt, about 1,000. Median other debt, about 2,000. And then you see minimum and maximum. So the minimum income is 12,000. The maximum is 1 million in the sample. The minimum credit card debt is 0. The maximum is 36,000. Minimum other debt is 0. Maximum 63,000. Okay, so here's a summary of what I've just said, just to have, so you have all these pieces in one slide in case that's helpful to you. The different measures of central tendency: mean, median, mode. Measures of dispersion: standard deviation for sample data, standard error for population estimates. Skewness: extent to which the distribution is slanted to one side or the other. Now let's talk about the reliability and validity of measures. It's a different topic, also very important. Reliability refers to the consistency or precision of a measure, while validity refers to its accuracy. So it's easiest to understand this in terms of bullseyes and how accurate or consistent we are in hitting a target. A reliable and valid measure is on target all the time. So our measure accurately represents the construct of interest and it is consistent. But it's possible to have a reliable measure, a consistent measure, that is not valid. That is, it consistently misses the mark. It is consistent, but it's consistently wrong. And then measures that are inconsistent are neither reliable nor valid. They're all over the place. So this is, for me, a very useful way to understand the difference between reliability and validity, and also to understand how they work together. So these ideas also map on to this idea that error can be either systematic, that's bias, or random. So systematic error is a distortion always in one direction. We're always wrong in a certain way. That's bias, systematic error. Random error is inconsistency. Okay, there's not a systematic pattern in the target on the right. We're just all over the place. Random error. So here's some examples. Social desirability bias is a systematic type of error that can affect self-reports, particularly self-reported substance use. So if you ask people about their substance use, they're likely to underestimate their substance use and try to make it look good or socially desirable. That's a pattern that we see in the data, a consistent bias in one direction. If our questions are unclear, that will introduce random error as people interpret the question in different ways. In measurement, when we talk about psychometric properties of measures, we're talking specifically about their reliability and validity. That's what psychometric means. It's not some psychological construct. It's about reliability and validity. So let's talk about different types of reliability and then different types of validity. There are three main types of reliability, and they are inter-rater reliability, which refers to agreement between independent observers of the same phenomenon. Test-retest reliability refers to consistency of a measure over time. And internal consistency refers to agreement between multiple items in the same scale. So let me break this down for you a little bit more. So inter-rater reliability, agreement between independent observers of the same phenomenon, is important because there are legitimately different perspectives on the same phenomenon. So I love this cartoon. One person says there are 4 legs, the other person says there are 3. In this situation, they're both right. But if we want to measure something consistently, reliably, we want different people looking at it to see the same thing. If we want to measure their lived experience, we don't really care about agreement. Okay, so whether inter-rater reliability matters depends a lot on what kinds of questions you're asking, because different perspectives can produce legitimately different responses. Test-retest reliability refers to the consistency of a measure over time. And here again, we have to think carefully about whether test-retest reliability is something we want in a measure. If I'm interested in measuring somebody's mood, it's not realistic for me to expect that that's going to be consistent day in and day out. Mood changes from day to day, week to week, sometimes hour to hour. So what's realistic to expect in terms of consistency of a measure over time depends on how you understand that phenomenon. My mood probably is going to be pretty consistent within a 5-minute period, but not necessarily over 5 days. So when researchers look at test-retest reliability, they should always tell you what interval of time they're using so that you can judge whether it's reasonable to think that that phenomenon will be stable over that time period. The third type of reliability is internal consistency, or agreement between multiple items in a scale. So typically we'll have a scale. In this one we're suggesting that it has 6 items. They're all supposed to be measuring the same thing, so they should all be highly intercorrelated. We'll come back to this. I don't expect you to fully understand this graphic just yet. You might, though. Now let's talk about different types of validity of measures. So the first sort of easiest kind of validity to establish is called face validity. And this really asks, does the measure seem to capture the construct of interest? Is it logically related to the construct of interest? Or is it capturing something completely different? And content validity is a little bit more complex. And here the question is, does this measure tap all of the important content, all of the domain of the construct of interest, and nothing else? Concurrent validity is asking whether a measure is associated with another established measure of the same construct. And predictive validity means whether a measure predicts results on some outcome or expected criterion that is thought to follow this predictor. So let's break this down again. Face validity. The measure appears to capture the construct of interest. So for example, there's a measure called the MST Treatment Adherence Measure, or TAM, that is intended to measure whether treatment was delivered following MST, a particular program, multisystemic therapy guidelines. So MST is a branded intervention that has a manual that shows how this intervention is supposed to be delivered. And then clients and clinicians are asked questions on this TAM measure, and the results are used to interpret whether or not MST was delivered as it was supposed to be. But this instrument, the TAM, includes questions about client satisfaction and outcomes, which really could be asked about any treatment. Clients could be satisfied with any treatment. They could have improvement because of any treatment. This has really nothing to do with whether treatment was delivered following MST guidelines. So on the face of it, this is not a valid measure of fidelity or adherence to MST. Here's another example related to content validity. So a measure should tap all of the content, the domain of this construct, and nothing extraneous. Well, here's an example. The Beck Depression Inventory includes questions about somatic or body experiences, affective, emotional states, and cognitive signs and symptoms. So it's thinking, feeling, and physical symptoms, and no other content. But so it's not just about mood, it's about body, mood, and thinking, because the construct of clinical depression, as it's defined in the DSM, has all of those components. Lack of energy, disturbance in sleep, disturbance in appetite, weight, mood, and focus are all signs and symptoms of depression. So the Beck Depression Inventory has good content validity because it does tap all of those constructs and nothing else. Another type of validity, concurrent validity. The measure is associated with another established measure of the same construct. So concurrent validity is often important when we're trying to develop a short version of an established measure to use in practice settings. And here we assess how well responses on the new measure correlate with responses on the established measure. And typically we do this by administering both measures to the same people and then simply seeing how well they correlate. If our new measure correlates very well with responses on the old measure, then we say it has concurrent validity. And then finally, predictive validity. How well does a measure predict scores on some criterion or outcome of interest? So for example, a valid measure of satisfaction should predict future attendance or retention, right? We would expect clients who are satisfied with some program or service to be more likely to attend or stick with the program than those who are not satisfied. Another thing to think about in terms of constructs and variables and measures is this idea of underlying dimensions. So some constructs are thought to have several underlying dimensions or subcategories. They're complex. They're not unidimensional. So the number of dimensions in a measure can be assessed with a statistical procedure called factor analysis, or sometimes principal components analysis, that looks for sets of items that are highly correlated. Now, you don't have to fully understand this, but it will be helpful to you to understand this idea of underlying dimensions. So I'll give you some examples. So here's an example. There's this construct of the therapeutic alliance, which is meant to be the quality of the relationship between people in therapeutic endeavors. So the qualities of the relationship between a helper and a helpee. Now, this is operationally defined in a number of ways by different instruments, but let's focus on one way in which this is defined and measured, and that's the Working Alliance Inventory developed by Borden. And in this conceptualization, the therapeutic alliance is thought to have three important underlying components that are distinctly different, it seems, on the surface. And the first has to do with what are called bonds. And that represents whether the client and therapist like and trust one another. So on this measure, there are a series of questions that get at this liking and trusting phenomenon. And a second component is called goals. And this reflects whether the client and helper share the same goals for their work together or not. And the third component is referred to as tasks, which reflects whether the client and therapist agree on the steps that they need to take to achieve their goals. So on the Working Alliance Inventory, there are three subscales, and each has questions aimed at tapping each of these dimensions. But when we use this inventory in clinical samples with clients and therapists, we find that these three components are so closely related to each other that many researchers treat this as a one-dimensional construct. That's interesting. So three different ideas, but generally when a therapeutic alliance, when a relationship is going well, there are high scores on all three, bonds, goals, and tasks. When it's not going well, there tend to be problems in all of these areas. So empirically, the Working Alliance Inventory is often treated as a single dimensional construct, and that's valid because these things go together. It's interesting. Here's another example. Social desirability bias is sometimes assessed by a scale called the Marlowe-Crown Social Desirability Scale. There's a version of it called the MCSDS 13 because it has 13 items or questions in it. And this is thought to have two underlying components. So there are two different subscales to measure each of these components. One of these is called an agree good subscale. It means that people tend to agree with false statements that make us look good. And the deny bad subscale reflects the fact that people tend to disagree with true statements that tend to make us look bad. So in both scales, we're not telling the truth. In both scales, we're trying to look better. But these are two different phenomena, agreeing with false statements, disagreeing with true statements. Now, what's interesting to me here is that these two components of social desirability bias, the two subscales, are highly correlated in some populations, such as college sophomores, and not in others, such as child welfare clients. So in college sophomores, social desirability bias involves agreeing with things that aren't true to make you look good and disagreeing with things that are true to make you look good. In child welfare samples, however, particularly among parents of cases of child abuse and neglect, people don't seem to care about trying to look good, and they do care quite a bit about avoiding looking bad. So the agree good and deny bad scales are not correlated. There are two different components of social desirability bias in child welfare samples, and really one underlying dimension in college sophomores. So here's an exercise for you to work on outside of and inside a class, understanding reliability and validity in an empirical study. So take a look at this article. It describes the reliability, validity, and sensitivity of a scale to assess practitioners' familiarity with evidence-based practice. And here are some sample characteristics and background variables of the practitioners in this study, 511 students and practitioners. And see if you can understand these M's and SD. M is mean, SD standard deviation. What do these data mean? See if you can understand what the frequency and percentage mean. And describe this sample in your own words. Okay, now let's interpret the results of their reliability and validity test. Coefficient alpha is a measure of internal consistency, which is our third type of reliability. Coefficient alpha ranges from 0, meaning there is no association between items in the scale, to 1, meaning there is perfect agreement between items in the scale. So here we have a number of scales with different coefficient alphas. Higher is better. Okay, so these data are used to describe reliability, averages, and standard deviations. Let's switch gears now and talk about qualitative analysis, which takes a different starting point, and that is creating concepts from observational data instead of defining concepts in order to measure observations. Okay, so we're going to flip this on its head now. Most of what I've talked about so far has to do with structured and mostly, not entirely, quantitative measures. But if I'm doing naturalistic inquiry, that's not the process. I'm going to start with raw data, and this is text, narrative, observation. And I'm going to go through a series of sort of iterations in coding and making sense of this data in order to create concepts. So the coding of raw data from text or observations begins with this sort of what they call level 1 coding, which is an initial open coding scheme. So here we have a lot of data, and we're focusing on labeling it and beginning to grapple with the data, its nuance and meaning. And once we've done that, we typically make a second pass that's called level 2, more focused coding, where we're beginning to develop categories, and now we're sorting it more actively. So we'll re-examine our level 1 codes and further focus, categorize, sort the data. Then we make a third pass, level 3 coding, axial or thematic coding. And now we're refining themes from the previous categories. And then maybe from that we will create theoretical concepts. These would emerge from saturated categories and themes that are consistently and richly represented in the data. So this is a very different way of going about developing constructs and categories from data. Equally important, equally valid, with very different uses. So along the way, in doing this kind of coding, we're going to create coding trees, and we're going to stick with them and refine them as we go along. But the coding trees will describe our budding system of categories and codes. Let me show you some examples of how this has been done. So this is an example from a study that I was involved in a long time ago. It's interesting. This is actually in the context of a randomized experiment to test the effects of intensive in-home services for families of abused and neglected children. And it's a very complex study that involved surveys and longitudinal data and random assignment to different interventions. But this example is a qualitative analysis that was embedded in that larger study. So for every single family in this study, and there were more than 6,000 families in this study, we asked the social worker, primarily responsible for the case, to tell us the 5 most important objectives of their work with this family. And we asked them to do that at least 2 different points in time, shortly after intake and then 3 months later. And we gave them these sort of 5 lines to write on. Just what are the 5 most important objectives of your work with this family? So 5 open-ended lines. They could write anything they wanted there. And then we coded the data. The researchers coded the data. And what we wanted to do, we wanted to get out of this several things. We wanted to identify different topics. So what was the nature of the problem they were grappling with? What was the topic or the focus of the intervention? So was it about housing conditions? Was it about income or subsidies or mental health, parenting skills, child behavior, children's living arrangements, etc.? What was the substantive topic? We also wanted to code whether this objective specified a process, something that should be done, or an intended outcome, something that should be achieved, or both. Because we noticed that these objectives were mixed. Some of them were about process, some of them were about outcomes. We also wanted to code who was responsible for achieving this objective. Is this something for the parent to do, or the child, or the social worker, or another agency? And we wanted to code the specificity of the objective. And we tried to do this on a 5-point scale. But here the idea was that more specific objectives would be more likely to be attained. So a worker could write, let's say they wrote 5 different objectives on each line, and each objective could be associated with each kind of code. So for any given objective, we could have a topic code, a process outcome code, a responsibility code, and a specificity code, all on the same line. So the results are a series of dichotomous variables describing content. Was this content about housing? Yes or no? Was it about income? Yes or no? Was it about mental health? Yes or no? And a series of dichotomous variables about process outcome. Was it process? Yes or no? Was it outcome? Yes or no? Same thing with responsibility. Who was responsible? Interestingly, although we, and there's a team of 40 people working on this study, tried very hard over a period of 2 years to come up with a reliable and valid way of coding specificity of the objective, we never got there. We could not come up with a 5-point scale that could be reliably administered by using inter-rater agreement by 2 different people looking at the same objective. So we decided if we could not come up with a reliable measure of specificity among ourselves, we shouldn't do it, and we dropped it. Might be fun to talk about that exercise a bit more in class, but here's some of the results of that exercise. This is a page from a book on this study, and these are the content codes. So the content of case objectives fell into these different categories, and here you can see we showed how many of the family first, that's the treatment group, or the regular services comparison control group, had objectives in each of these categories. So even though there was a lot of different content, social workers were working on a lot of different issues in these cases, we did get reliable codes for this content. So what that means is that two different researchers looking at the same handwritten objective by a social worker did agree on these content codes. So let's talk a little bit about qualitative and quantitative data. We have structured and unstructured measures. So surveys tend to be structured, and interviews can be structured or unstructured. They can both produce qualitative and quantitative data. So in a structured survey, I can have both qualitative and quantitative responses. Quantitative data are numeric. Qualitative data are not numeric. So again, I could ask you, to rate something on a scale of 1 to 10, and then to write in your comments about it. Well, your rating is numeric, it's quantitative. Your comments are not, they're qualitative. Sometimes qualitative or non-numeric data are represented with numbers, but this doesn't change the fact that the data are inherently qualitative, meaning non-numeric. So here's an example, religion. Yeah, these categories are different, they have meaning, but the meaning is inherently non-numeric. Okay, in critically appraising studies, we always have to think about their key constructs. And here are some essential questions to ask in critically appraising research of almost any kind. Are the constructs clearly defined? Is it clear what phenomena they're interested in? Are the key constructs grounded in either theory or empirical observation? And then for structured measures, is the level of measurement appropriate for the construct, or is there a mismatch there? Is there evidence of reliability of the measure? And if so, what kinds of reliability have been established? Is there evidence of validity of the measure? Is it accurate? And if so, what kinds of validity have been established? For a more naturalistic inquiry, the development of themes or constructs from text or observations, that bottom-up inductive work, we would ask different kinds of questions. And here I would ask, is the process of data collection and coding clearly described? Do we understand how they made observations, how the data were collected and coded? And is the development of main themes or concepts clearly described? Okay, that's it for now. Talk to you soon.